Hey guys, today I'm going to show you about the dimension keyword in PyTorch. Even if you just started with deep learning, you will see this a lot, the dimension operations, and it may be confusing on what it stands for or what are the differences when you change the dimensions or how it works, how it operates. In this video, I will just go through everything. We'll start with one-dimensional tensors. We will move to the two-dimensional tensors and use the knowledge we gain with the one-dimensional tensors. Then we will move to the 3D dimensional tensors, and we will build on top of the previous examples we did with 2D and 1D tensors, and we will move on additionally to the 4D tensors. After that point, you will see that how easy it is and how you can build more dimensions, and you will understand how things are operating. We'll do manual calculations. We will just take tensors, do the dimensional operations, and we will do them by hand, and we will execute the code and verify that we did correctly. In general, we will be using the sum keyword because it is widely used and see what is going on, but the logic is the same if you use any keyword with Torch, as long as you have the dimension. And also to demonstrate it further, I will also do an example with another keyword which is called any. So I suggest you to watch this video from the beginning to the end, because we will build on top of the previous things we did throughout the video, and in the end you will have a concrete understanding of what's going on with the dimension keyword within PyTorch. Before we begin, make sure to like this video, subscribe to my channel. What you want to see next, just comment out in the comment section below. I will also put the GitHub link for the code we used in this video in the description below, so you can just check out and follow that with me. And if you're ready, let's just get started. Since you are going to work with PyTorch tensors, obviously the first thing we are going to do is we will import PyTorch, and actually this will be the only thing that we will import. Go through by analyzing the smaller parts first, such as this one-dimensional tensor, basically a list, and we will build our way gradually to the bigger picture. So stick with me. This one is going to be simple. We have a tensor. This is a 1D tensor, just like a list. And first we will check its shape. Then we will apply our sum operation, which is going to be summing the dimension 0, which we will work on dimension 0. Since this is a 1D tensor, it has a one dimension anyways. So you can see what S will be in this case. It will be just the summation of these numbers, of these elements here. So don't forget, if we go to the smallest building block, which is a 1D tensor, we just sum up its elements. We will use this information when we are working with higher dimension tensors. And just let's print S, and let's also print the shape of our summed tensor. So no surprise, the shape of this is 5 since it has 5 elements inside. S is 15 since the numbers here add up to 15. And the torch size is empty because we end up with a scalar. Now let's increase the dimension by 1. Let's create a 2D tensor. We can do this basically like this. So this bracket is just what encapsulates everything. So you don't need to really care about this bracket. We can also put it to here. We also use it in the 1D tensor as well. It just encapsulates everything. When we look at a tensor like this, how do we see its dimensions? It's just we go from the outermost layer to the innermost elements, and we just count it. So as you can see, there are 2 chunks here. One is this, and second one is this. Basically, there are 2 elements, and every element has 3 more elements in it. So this will be a 2 to the 3 tensor. Let's actually verify this by printing the shape of it, which is correct. It has a shape of 2 to the 3. Now let's actually do some calculations using the dimension. Let's start by dimension 0. Let's say that we do a sum operation. By the way, I'm doing a sum operation, but like I mentioned, it can be any operation that uses these dimensions, because the logic is the same. I am giving you examples with the sum torch.sum operation because it is widely used and it is just easier to observe what's going on. So when we work with tensors with more than one dimension, the smallest dimension means the outermost element, and as we increase the dimension, when we do 1, we go to the innermost elements gradually. So when we say dimension 0, it means that we are working with the outermost elements. And how do we see what the outermost elements are? It is simple. We just look at the biggest elements. The biggest chunk elements is these two lists over here. So when we say dimension 0, we say we are going with the outermost element. So here, in this case, these are the outermost elements. You can just say that this is the first bracket we encounter, excluding this, because this is just encapsulating. This is the outermost bracket, so this the outermost elements. This is also another way to look at it. What this will do when we say torch.sum dimension 0, which is the outermost elements, is basically it will add this list with this list. So it will look something like this. So you can think of it like this is a just basic addition by writing one under the other. So it will be basically 5, 7, and 9. This is just how it is done. So let's print this dimension 0 dot shape. So we did actually the operation here. So what we expect for dimension 0, which is the result of this to be, is this tensor, which is 5, 7, 9. Let's also add this shape, which is tensor.size to the tree, the shape of our original tensor. And the shape of this is, since it is just a list, as we did at the previous step, we expect its size to be just this one. And let's just verify. Sorry, we expect this to be this one because it has 3 elements. It is not a scalar. Sorry for the confusion. So we can verify that what we did is correct. So this dimension 0 is 5, 7, 9, and it has a size of 3. So as you can see, it is pretty simple. You just go to the outermost elements when we are working with the smallest dimension and you just add them up. So let's just remove these. Since this is a 2D tensor, we can do the same operation with the dimension 1. So let's do that. For dimension 1, we are going to apply the sum operation for the dimension 1. So how do we do that is, remember, we are moving from the outermost element to the innermost element. So when we do it with dimension 1, it will be just elements of the list itself. And when you think about it, we actually did this operation with elements of the list in the previous example with the 1D tensor. You remember what we did? We had this list and we just added these elements up. So here we are just going to do the same thing with dimension 1. This was dimension 0. The innermost element of it is just basic elements of the list, which is just the operation we did previously. So what we're going to do is we will add these elements of these tensors and we will end up with 3, 5, 6. This is one element. And 5, 9, 15. So torch.sum will be tensor 6 to 15. And let's print it to check out if our code calculations were correct. And let's get its shape also. So if you look at it here, it is just size of 2 since it has 2 elements. So we expect it to be torch.size 2. And let's print it and let's verify our answer. So for dimension 1, the dim1 tensor is 6 to 15, just what we did here, just adding up the innermost elements, and its size is 2 since it has 2 elements. One more note here, you will see a lot of the times, you will see this notation, dimension, let's say special, equals the torch.sum tensor dimension -1. So what does dimension -1 means is basically it means the innermost dimension or the last dimension. It is just like list. When we access an element of the list and we say -1, we access to the last element. It is the same with dimension. When we say -1, we access to the last element. So what this is, actually, it just means dimension 1, since dimension 1 is the last dimension of this tensor. Also, we can just verify it by doing some print statements. Let's just say print dimension -1, print dimensions, which is the result of the -1 dimension, which we expect it to be the same with the dimension 1, since it is the last dimension, and size it to be 2. Let's print and verify, and let's add an additional print so that it will look prettier. So dimension -1, as you can see, it is just the same as the dimension 1, which is the last dimension. So we did it with 2 dimensions. Now let's move on to work with 3-dimension tensors. And if you can see that we are just building everything on top of each other. For 2D, we used our first example, which is the 1D tensors. Now, for explaining the 3D tensors, we will just use the logic we gained with the 2D tensors right here. Let's create our tensor and let's see that if we can get the dimension of this tensor. So when we look at it, there are two outermost chunks, as you can see. Also, you can go with the parentheses at the outermost layers. So there are two of them. So it starts with the dimension 2, and each of every one of them, there are two elements or two parentheses, and each of them has three elements. So we have two elements in the outermost layer, as you can see here, and inside each of these elements we have three more elements. So its dimensions will be 2 to the 2 to the 3. You can go by counting brackets, like 2 brackets, 3 elements, or you can just look at the commas. But overall, when you look at it, you can just see that it has two outermost elements, so it means dimension 2, and each of them has two more elements, and each of them has 3 more elements, so it will just give you the dimension. Let's also verify by printing the tensor.shape. So we expect this to be TensorTorch.size 223. Let's print it, and yes, we calculated the dimension of this tensor correctly. Now let's continue with doing some operation using the dimensions of this 3D tensor. Let's start by, as usual, dimension 0, which is the outermost dimension. And again, let's do our sum operation with the outermost dimension. As you remember, what we did the previous time, we just took these two outermost elements and just added them up. So guess what? We are doing the same thing again with, the outermost elements. So what are the outermost elements of this tensor? One of this is this, and the other one is this. So when we add them up, what we get is 6, 8, 9, 10, 12, and 2. So which we expect dimension 1 to be actually this tensor. Let's print it and let's write what do we expect. And also let's print its shape. And from the shape, what do we expect is, when we look at that, this is the encapsulating bracket. It has two elements from the outermost, and every element has 3 elements inside. So its shape will be 2 to the 3. Also, this becomes the tensor that we just worked previously. And let's verify our answer. And we did it correctly. As you can see, it is 6, 10, 9, 10, 12, 2, which is what we did here, and its shape is 2 to the 3. Now let's work with the dimension 1. So what's going to happen when we say dimension 1 is that instead of taking the outermost elements, which is these guys, we just step in for one time. In this case, our elements are these and these. First of all, what does it look like is, it is a 2D matrix, and so basically it's an operation on this 2D matrix. So with these elements, when we do the operation, we just, as we did before, we just take this, and we are going to add them up. So let's just take these guys, and when we add them up, they become 4, 6, and 9. And we take the other element and add them up, and they become 12, 14, 3. So this will be the result of the sum operation on the dimension 1. Like I said, it doesn't have to be sum, but when you do any operation with the dimensionality, you will use this same logic. So let's print dimension 1, and as we did here, we expect its output to be 4, 6, 9, 12, 4, 3. And its dimensions will be, if you look at here again, it has 2 outermost elements, and every one of them has 3 elements inside. So we expect its dimensions to be 2 to the 3. Let's remove these and let's verify. And let's put one more print here so that it looks pretty. Yes, dimension 1, 4, 6, 9, 12, 14, and 3. So we did the operation correctly, and the size is 2 to the 3. So we did that correctly as well. And now let's move one more dimension, which is the last dimension we can go. since this is a 3-dimensional tensor, we can only go for 3 dimensions in total. So we can go at most to dimension 2. So at the last time we worked with these elements, and now we go one more step in. So if we go one more step in from these elements, we end up with these elements. And this is what we actually did in the beginning with 1D tensors. So when we did do these operations, what we will end up with is we have to add these up, which is 9, 11, 12, and we have to add these up 7, and we have to add these up 11, 12, and we have to add these up, which is 15, 17. As you can see, it is pretty straightforward. We just move one step inner, we do the operations, and that's it. So we expect this to be the tensor 12 to 7, 12 to 17, and its dimensions would be 2 to the 2, as you can see here. And let's remove these and let's verify our answer and add another print statement so that it looks pretty. So for dimension 2, 12 to 7, 12 to 17, which is just what we did, and torch.size is 2 to 2. Now I want you to also realize another thing. So when we do an operation on the dimension 0, for example, we end up with a torch of size 2 to 3. So how you can see the end size of a tensor is that our original tensor had size of 2 to 2 to 3. And when we do an operation at the dimension 0, means that we are just summing that whole dimension up, so that that dimension will be gone because it is consumed in the summation operation or any other operation you are doing. So when we are doing an operation on the dimension 0, if you want to see the final dimension of this dim 0, you can just remove the 0th element and it will give you the dimension, which is 2 to the 3. So if we do it with the first dimension, then you go to the original tensor size and you just remove the first dimension. What is left is 2 to the 3, so it will be the dimension of your tensor. So let's do it also for the second dimension. So we will just remove the second dimension and we will end up with 2 to the 2, which is the case, because these dimensions are getting consumed during the operation we are doing. So we can verify this with our previous examples as well. So if we go here, the experiment we did with 2D tensors, its size was 2 to the 3. So if we do an operation at the dimension 0, we just remove this 2 and we end up with a torch that's size 3 as its dimension. If we do an operation in dimension 1, we just remove this 3 over here, which is dimension 1, and we end up with torch that's size 2. So this is the way that you can actually, without calculating anything, you can just see what your output dimension will be. And this is how it is done for a tensor with dimension 3. And this is the basic logic. When you increase the dimensions, nothing changes. You just do the same operations by adding one more dimension. And let's just put everything together. Let's actually do one more example with a 4D tensor, and let's just apply everything we learned. So nothing will change, we will just do the same things, but we will do for one more dimension. So let's create a 4D tensor. In this case, it will look like this. This is our 4D tensor, and as we did before, let's start by calculating its dimensions. So it may look like a long and complicated tensor, but as I said, this is the same operations that we have been doing, just adding one more dimension. That's it. Let's start again by counting the outermost elements. So this is one outermost elements. Again, you can just look at the elements and see that this is a one big element, or you can go for the brackets or commas, whatever. So this is one of them, this is the second one, and this is the third one. So the dimensions of this tensor starts with 3. Tensor, it starts with 3. And we take one step to the inner element. So this was the most outer element, one of them, and we take one step in, and we have 2 elements here, as you can see. First one and the second one. So the second dimension of this tensor is 2. Also, I want you to realize that once we did that, this is just a 3D matrix, which is what we did before. So that's what I mean when I say we just go incrementally and we just add one more dimension. And when we go one step inside to this element as well, we see that it has 3 elements. So the third dimension is 3. So we put 3 here. And inside this, every element here, it has 2 more elements. So the final dimension is 2. So as you can see, it is pretty much straightforward. We are just doing what we have been doing so far. And let's just verify this by printing tensor.shape. And what we expect is this one that we calculated, which 3232, which is the correct calculation. And now let's move on to doing operations using dimensions. So let's start by, again, the outermost dimension, which is the dimension 0. So what is the outer dimension in this case? So this is the outer dimension matrix. So what we are going to do is we will basically just take these guys and add it with these guys and add it with these guys. Again, what we have been doing so far. So what we will end up with is, let's actually put this here. It is very simple. We will just take, this is the 0th element of that, the outermost element. So we add these up, 1, 4, and 9. And we add these up, 2, 6, 12. And let's also mention that since these have 2 elements and we are adding 2 more elements, this will have an outer dimension as well. So it will be actually look like this. So now we are just doing the operation for one of its elements. So we are right here. This was the first one. Then we add these up, 3, 8, 15. And when we add these up, 4, 10, 18. Again, the same thing, 5, 8, 13. 6, 14, and 14. So this is not 13. I realized I did a calculation mistake. It is easy to miss this. 5 added by 7, 12 added by 9 is 21. So this is actually 21. So we take these big chunks and edit the 0th elements, and now they have 1 more element, so we have to add these up. So this was the first element here, and now we are going to add the other ones. So I'm not going to do them again, but it is the same thing. You just take the 0th elements of the first element and add them up. And when you do the operations, this will be the output for the second elements. Let's actually verify that. First, let's print the dimension 0. So what we expect is exactly this here. So let's put this here. So let's look at the shape. Again, we are doing the same things. These are the encapsulating brackets. So we have 2 elements here, 2 outermost elements. So its size will start with 2. Each of them has 3 elements. It will go by 3. And each of these elements has 2 more elements inside. So we put 1 more 2 here. And let's verify if our calculations are correct. Let's also remove this. And 9, 12, 15, 18, 21, 14, 17, 10, 13, 16, 9 to 12. Which this is correct, and torch.size is 232, 232. This is also correct. Now let's move 1 more dimension and let's go for dimension 1. And let's do this operation for the first dimension. What it means is that instead of taking these elements, we are working with these elements. We are working with these 2 elements here, which are, again, just 3D matrices. So we will just do what we did before. Also with other examples, specifically the previous example, we will just take this, and add them up together. We have a 1 big encapsulating tensor, and we have 3 elements here. We will do this, this, and this. So first one is we are just going to add this and this, which we end up with 8 to 10. And then we are going to add up this and this, which end up as 12 to 14. And we are going to add this and this, which end up as 6 to the 8. 6 to the 8. And then we move on to the other one, and we do the same operations. Now we are in this, which is this and this. So this is 12 to 4. This and this. So this is 6 to 8. And this, which is 10 to 12. And we do the same thing for the last one, which I'm not going to do, but it's the same thing. You take one element here, add them up here, add them up, here, add them up, and it results as this. And let's put our results here, which is 8, 10, 12, 14, 6, 8, other element 12, 4, 6, 8, 10, 12, etc. and ends up with 14 and 6. And let's print our dimension 1, which we expect it to be this. And let's print the dimension 1 shape. So we discussed how we can just get the shape of it, and let's just use that. This is our original dimensions, so we are working on the dimension 1, so we will just squish those elements, and the dimension 1 will be removed from the final dimension of the tensor. So the original shape is this, so we just remove the 2 here. In the end, we end up with dimension of 3, 3, 2. And let's just write it. Torch.size 3, 3, 2. And let's verify this. And let's put a print statement here so that it will look pretty. 8, 10, 12, 14, 6, 8, etc. which is correct. And the size, we expect it to be 3, 3, 2, and it is 3, 3, 2. Now let's do it for the dimension 2. Last time we worked with these two guys. Now instead of that, we move 1 inside again, and we are dealing with these guys. So we will just add these guys. Let's also remove this. So how this will be is that again we will have 3 elements, and we will just add these up. So it will be 5, 8, 9, 10, 12, 7, 9, 1, 17, 18, 12. And we move on to the next one, which is the same thing. We add these up, 10, 15, and 18. And if you have realized, we have just started doing the operations that we did at the previous examples. And let's now do this, for this, 9, 10, 13 to 6. The same thing, I'm not going to do it. 21, 14, 9 to 12. So again, let's verify this. Let's print dimension 2, tensor 9, 12, 17, 20, 15, 18, 13 to 6, 21, 14, and 9, 12. And again, let's try to predict its shape. So we are working with the dimension 2. So this is the second element. This will get squished. So in the end, we will end up with 3, 2, 2, and we wrote it to here. And let's actually print this. And let's also add a print statement here so that it looks pretty. So for the dimension 2, our elements are 9, 12, 17, 20, 15, 18, 13, 6, 21, 14, 9 to 12. And the size is 3, 2, 2. 3, 2, 2. So we did this correct as well. And let's do it for the last dimension. Let's remove this. We are working with the innermost elements. So it means that we go just what we did in the beginning, and we will just add these guys up. So it will be, again, the bigger matrix, the bigger tensor, and inside that, it will be 3, 7, and then you add this is 11. And we have one more dimension here that I forgot to put. Okay. And we do the same thing for this. 15, 19, 3. 15, 19, 3. And we move on to the next one, which is 7, 11, 15. 9, 3, 7. 9, 3, 7. And the last one, 11, 15, 9. 11, 15, 9. And 3, 7, 7, 11. 3, 7, 11. And this will be the result. Then let's say print dimension 3 and let's just verify, which will be 3, 7, 11, 3, 7, 11, 15, 19. 3, 7, 11, 15, 9, 3, 7, 11, 15, 9, 3, 7, 11, which what we calculated here. So let's remove this, add our additional print statement here, and let's print the shape of dimension 3. So we squished the last dimension, so we will end up with only this. So what we expect the dimension to be is 3, 2, 3. So this is what we wrote here. And let's just print it and verify. So 3, 7, 11, 15, 19, 3, 7, 11, 15, etc., which is the correct output, what we calculated. And the torch.size is 3, 2, 3, again, what we calculated. And again, just as a reminder, you will see a lot of this. Torch.sum, tensor dimension -1. This -1 just means the innermost dimension. For example, in this case, it is 3. So this is exactly the same thing as this. If you see that, just don't get confused. So far, we have only used the sum operation, but I said whatever you use, the logic is the same. And to make things more complete, let's make an example with an operator called any. So what any does is that we give a tensor and a condition, and it will just check them and it will return true if that condition is met. So the only difference we have now in this example is that instead of sum, we will do this any operation, and instead of adding elements, we will just check if there is an element that is less than 2 between the elements that we are doing the operation on. So instead of adding elements, we will check if element is less than 2. Instead of the summation, we will return true or false. So let's do it for the dimension 0, starting with outermost dimension, which, as you remember, these and these. So instead of doing the summation, we will just take elements and see if the condition is met. Remember what we did with the 3D tensors. These are our two outermost elements, and since we are working with outermost dimension, we will do the operations on them. So we will start with these guys. So 1 and 5, instead of adding, we will see if any of them is less than 2, which is 1 is less than 2, so we say true. We look at 2 and 6, none of them are, so we say false. We look at 9 and 1, 1 is less than 2, so we say true, and we move on. 3 to 7, none of them is less than 2, so we say false. 4 to 8, none of them are less than 2, so false. 0 to 2, 0 is less than 2, so we say true. So let's print dimension 0, which is true, true, which is true, false, true, and false, false, true. And the dimension, the shape of it is, again, we remove the first element since we squashed it. As you can see here, instead of these two elements, we have one element. So we have 2 to the 3, and let's print and verify. As you can see, true, false, true, true, false, true, false, false, true, false, false, true. So this is good. Let's do it for the first dimension. Let's remove this, and when we say first dimension, now we are working with these guys. Again, instead of any addition, we are just going to do true or false. So 1, 3, 1 is less than 2, so this is true. 2, 4, none of them are less than 2, so this is false. 9, 0, 0 is less than 2, so this is true. Let's make it like this. 5, 7, none of them are less than 2, so this is false. 6, 8, none of them are less than 2, so this is false. 1, 2, 1 is less than 2, so this is true. And this is what we expect when we print dimension 1. True, false, true, true, false, true, true, false, true. Sorry, true, false, true, false, false, true. False, false, true. And let's print the dimension 1 dot shape. So we just remove the dimension 1 and we end up with 2 to the 3. And let's put our last print statement and check. So true, false, true, true, false, true, false, false, true, false, false, true, and the shape is 2 to the 3. So this is correct. And let's do it with dimension 2, because the torch.any dimension 2. Let's remove this. So now we are working with the innermost elements. So we will simply say if there is an element that is less than 2 here, which there is 1, so we say true. We look at here, there's an element less than 1, which is 0, which is less than 2, which is 0, we say true. Let's make it like this. And now let's look at here. Is there an element less than 2? There is 1. So we say true. Here, if there is an element less than 2, no, there are no elements less than 2. So we say this is false. And this is what we expect from the dimension 2. True, false, true, true, false, sorry, true, 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 false. So we expect this, which is this, and let's print the dimension. So we are working with the last element, so we will just remove this 3 and our dimension will be 2 to 2. And let's verify this. So true, 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 false, true, 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 false, and the shape is 2, 2. And that's it. We did dimension operations up to 4 dimensions, and we did them as exercise. We did manual calculations. We did with multiple operations. We used sum and we used any. And as we have realized that we just started with the smallest unit here, and we just like recursively, we built on top of it. We increased the dimension by 1. And use the previous example, we increase dimension 1 more, use the previous example, etc. And we built on top, we did the calculations by hand too. So if you want to move more dimensions, you just know what to do, you just repeat these operations. We also did, instead of sum, we did with any, so that to show you, you can do it with any operation. The logic is same as long as you are using the dimensions. And you will see this dimension -1 frequently. It just means the innermost dimension. So this one, in case of 2D matrices, the same as this one. I believe we covered everything, and I hope you have a concrete understanding now on how dimension operations are working within PyTorch. And thank you for listening. Don't forget to like this video and subscribe to my channel. See you at another video.